Right, good day to everyone. And for this session, we will be talking about Aquifer Geology. And this is more on using geology as a tool on how we can build up our expectations, or it's about using geology to build a model on how an aquifer may behave in terms of permeability, porosity, and other hydraulic characteristics. All right, so this is all about starting with the more or less the genesis of your aquifer and using those clues to build up our understanding on the aquifer. Now, there are three main groups. All right, first is your unconsolidated sediments, which are mostly your soils and some rocks that are too soft to be considered rock by engineers, so they're considered as sediments, such as your ash or tuff or heavily weathered basalt, right? So those are still considered as unconsolidated sediments in hydrogeology. We also have sedimentary rocks, right, which is chiefly comprised of sandstone and other types of sedimentary rocks. And finally, you have your fractured rock or your bedrock aquifers, which are all about aquifers that rely on your secondary porosity. So these are the aquifers that rely on fractures, joints, and faults and foliation as well for them to have an ability to transmit groundwater, right? Now, these groups are further subdivided based on their depositional environments, all right, especially for your sediments or for your unconsolidated sediments, right? Because they give us, of course, clues on how they may behave, right? So if you're expecting fine or low energy environment, you're expecting fine soils like silts and clays, and from there you can expect that your aquifers may have low hydraulic conductivity. Or if you are talking about high energy environments like mountains and alluvial fans where you can have sand and gravel, you will be mostly expecting materials with high hydraulic conductivity, right? Now let's start with the unconsolidated sediments group. You have your subtype comprising your sand and gravel aquifers. And this is further subdivided into the following. So you have your stream valley aquifers, which mainly comprise your aquifers that are lying on channels, floodplains, and terraces. Right? So your buried channels, right? So when you have river that is migrating, right, the old channels get buried and they can remain as aquifers, especially if they are covered in sand and gravel. You also have your floodplains, right? So you know that floodplains are more or less adjacent to your stream or your major river, and there's a lot of interaction between your floodplain and your body of water that is allowing them to have a lot of recharge and eventually store water. And you also have your terraces, right? So your terraces that are the remains of the progressive incision of your valley system, right? So terraces are your essentially they are your old floodplains that were cut down, all right? They were progressively cut down, and of course these terraces will contain silts, clays, sands, gravels. They contain an assortment of sediments, and of course, by proximity, they can also act as aquifers. Another type is your basin fill aquifers. These are commonly or these commonly involve your basins that are formed by normal faulting. Okay, so these basins are inland basins, right? So inland area that was normal faulted or was has undergone extensional regime. Okay, so extension or normal faulting will cause subsidence, tectonic subsidence in the area, and over time this subsided area will be filled with sediments, and the sediments eventually are um, as they are lying on a topographic depression, they eventually accumulate water from the surface and they eventually act as aquifers. The third type is your blanket sand and gravel aquifers, which chiefly pertain to your alluvial fans, right? So alluvial fans are your transitional areas, right? So alluvial fans represent the break between the mountain and the lowlands, okay? And these are the areas where you have an accumulation of sediments from your mountain areas, as well as, of course, your drainage path of your surface water. Okay, so your water also comes down from your mountains and they go down. They pass through the alluvial fans first before they go to the lowland. And finally, we have our semi-consolidated sand aquifers, which consist of coastal areas. So these are your sequences of sand and calcareous sediments, like arenaceous sands and as well as coralline limestones. Okay, and they also can also act as aquifers. All right. All right. Let's talk about the next slide. Now let's talk about the stream valley aquifers in detail. As mentioned earlier, they mostly involve your floodplain areas, and they are actually significant worldwide, and they are actually the most utilized type of aquifer for these three main reasons. First is that these aquifers mostly involve sand and gravel deposits, and sand and gravel, as you may know, typically have a lot of have a high interconnected porosity, or what we call effective porosity, which allows them to transmit a lot of water and store a lot of water at the same time. Second is that these deposits are mostly exposed at the surface, and therefore they have a direct connection to your surface water in form of precipitation, so they get a lot of direct recharge. Okay, and third, they are also getting additional recharge from nearby uh, surface waters, typically your streams and rivers. Okay, so to summarize, the importance of stream valley aquifers hinges on their high effective porosity and their direct recharge, and also the additional recharge that they get from adjacent rivers or streams. Now, this is just a block model of a stream valley aquifer located on a floodplain. And you can see here, right? So this is your stream, and this is your aquifer. And this more or less is your stream valley. And you can see here that your stream, all right, can directly uh, provide recharge to your underlying aquifer, all right. And also note that floodplains are your typically your areas where most of your runoff from your whole watershed are converging. So you can also expect a lot of surface runoff coming on or coming through this area, and they can provide direct recharge to your aquifer, right? You should also note that floodplains have a highly heterogeneous soil profile. All right, so if you would look at a 2D cross section of a floodplain, you typically have your stream here, and you will also have a lot of old channels that comprise your floodplain. And these old channels may contain a sequence of silt, sand, gravel, and so on, depending on the changing energy regime. And it's really difficult to just lump together the property of the aquifer in this area. So you can also actually expect a lot of perched aquifers, all right? Perched aquifers in your floodplain, which will typically reside on an old channel within your floodplain, all right? In addition to your deeper aquifer, right, lying underneath. All right. Now and this is a photo of another example of an alluvial aquifer in Serbia, which has one of the largest well fields in the world. Okay, so you can see here you have two rivers. You have your Savar River and your Danube River, right? And this area has a huge complex of groundwater wells, comprising of by as much as 99 collector wells and tens of vertical wells. So this would look like a network, right? So you have vertical wells, and you may have your collector wells, all right, that are branching out from your vertical wells. Okay, so this provides your well a huge connection to the aquifer in the area. Okay, so your collector wells are going laterally, and then you have your vertical wells that are uh, going that are connected with your collector wells. All right, next type is your basin fill aquifers, which, as discussed earlier, they involve depressions typically formed by tectonic means or simply by erosion. And the feature of this type of aquifer is that they are since they are surrounded essentially by mountains, right? So they are getting a lot of recharge from your surrounding mountain areas. Okay, and we call that your mountain front recharge. Though one of the risks with basin fill aquifers is that you have more or less water that is just accumulating and accumulating at depth, right? most of the water that is going out of your fill aquifers are going out through the surface, but when it is overflowing, and so the bottom of your basin fill aquifers are more or less untouched. Okay, so you can get a lot of concentration of minerals, even salts that can accumulate from yours. Okay, so your surface runoff will naturally have dissolved minerals, including salts, and they can accumulate on the bottom. And once over extraction happens, or once a deep well taps into the bottom of a basin fill aquifer, this can inevitably lead to the upward migration of your concentration of minerals, and including salts, and this can contaminate your uh, upper 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 parts containing fresh water. Right now, this is just a nice example of your basin fill aquifer, and it's just showing a block diagram, and this is your basin fill aquifer. These are your faults that form that depression, and here are your mountains that are providing the recharge. All right. And this is just another perspective of another basin fill aquifer. And you can appreciate here the contrast, right, between the flatness of this basin fill and the ruggedness of the surrounding mountains, which provide recharge to the basin fill aquifer. Okay, so there is definitely a distinctive geomorphologic pattern here, which is expressed by an abrupt change from rugged and steep mountain areas to a suddenly flat area. All right. Next type is our blanket sand and gravel aquifers. And sorry. So these are, as discussed previously, these involve mostly alluvial fans, okay, that are brought in from the mountain ranges and deposited in the lowlands. And these are essentially, this is your mountain range, right? So your sediments are flowing in your lowland, and you get your alluvial fans, right? So eventually you get overlap, so you can get alluvial fans all over the area, okay? And this can form a series of aquifers, right? Although you can also have a single alluvial fan comprising one blanket sand and gravel aquifer. So this aquifer can be comprised of a single alluvial fan or multiple overlapping alluvial fans. Right? This is just a block diagram of an alluvial fan, right? And a photo, an aerial photo. Next is your semi-consolidated sand aquifers, or your coastal plain aquifers. As discussed earlier, they involve carbonate rocks accompanied by semi-consolidated sand, silt, and clay. Okay, and these are formed by your sea levels that are going back and forth. Okay, so you have your transgressions and regressions, all right? Okay, so when you are having, all right, so you are having a series of transgressions and regressions. which will definitely involve changes in depositional environment. So you get high energy, low energy deposits in alternating sequences. So you can expect a lot of variability in the composition of your deposits, which in turn will affect their thicknesses as well as their hydraulic characteristics. Okay, so again, this will involve more or less highly heterogeneous materials. And another risk in these aquifers is that you are near the coast, which will have a lot of salt water. So when you start pumping in too much, once you start lowering the water table in this aquifer, okay, once if you end up lowering the water table of this aquifer, okay, you start forming a hydraulic gradient from the sea towards the land. All right, and of course you will get this will result in uh, saltwater intrusion. Now, this is an example of a coastal plains aquifer in the Atlantic in the US. And you can see here more or less a map. So it's a huge interstate aquifer formation, right? That is spanning their Atlantic coast, right? And this is a cross section, an exaggerated cross section of that aquifer. Okay, so this is your basement rock, and then you have various formations, right? Okay. Now let's talk about sedimentary rocks. All right, so your first type is your sandstone aquifers, and note that the surface of the earth, right, is or a huge portion of the surface of the earth is covered by sedimentary rocks, and the estimate is around 73%. Okay, so sandstone aquifers are right. So you have a lot of sedimentary rocks in the earth, and in turn, most of your sedimentary rocks are sandstones. Okay, so by that logic, you can expect a lot of sandstone formations in the earth, and therefore sandstone aquifers, right, are hugely abundant in the earth. Okay, so another feature of these aquifers is that they have really thick formations in order of kilometers. Okay, so you're talking about kilometers here, which is much bigger than what you'd expect in unconsolidated sediments. Okay, that typically your alluvial fans or your floodplain deposits, they typically range in a few tens to hundreds of meters and maybe a few kilometers, but mostly it's in the range of hundreds of meters. Alright, so another feature with sandstone aquifers is that despite their low permeability compared to their unconsolidated cousins, sandstone aquifers are, yeah, they're hugely abundant, they're thick, and they're huge in quantity. Okay? And their porosity will typically depend on the age and the diagenesis of your sandstone. So if your sandstone is relatively young or was not subject to cementation in their diagenesis, you can expect more or less a lot of primary or matrix porosity. while for your well-cemented sandstones, most of your porosity will be coming from their discontinuities or your faults, joints, foliations, right? So discontinuities is a favorite term of engineering geologists. Okay, so discontinuities are they are an umbrella term for any break in your rock. Okay, it could be fault, joint, fracture, foliation, bedding, or lenses. Okay, so it's a convenient term. Okay, all right. So to emphasize, sandstone aquifers are huge and abundant and thick, and some of them are even are continental in size. And these are the two important examples of your continental scale aquifers, your Guarani aquifer system or Botucatu aquifer in Brazil, Uruguay, Paraguay, and Argentina. Okay? So they cover an area of 1.2 million square kilometers. I think that's three times the size of the Philippines. And its volume is in the order of 40,000 cubic kilometers. And they have a lot of water and also a lot of recharge that Puri et al. In 2001 estimated that this aquifer system can supply water to 5.5 billion people for 200 years. All right. So this aquifer can more or less supply more than half of the current population for 200 years if you can live that long enough. The next example is the Nubian Sandstone Aquifer System, or the NSAS. And this aquifer is situated in one of the most troublesome areas in Africa. Right? So it spans Egypt, Libya, Sudan, and Chad. And this aquifer is huge, but uh, due to the arid or the dry climate in this area or in this region, the aquifer actually has a negligible amount of recharge. So it's getting some recharge, but people can't really rely on that recharge to replenish the aquifer. So this aquifer system is treated as a non-renewable source. Okay, so every amount of water that they get from this aquifer is actually uh, aquifer mining. Okay, so all the water that you get or extract from the system won't be replenished within the lifetime of uh, within within our lifetime. And this aquifer has an area of approximately 2.2 square kilometers and a volume of 372,960 cubic kilometers, which is very, very huge, like 10 times larger than your Guarani aquifer system. Okay? And it is estimated that the recoverable groundwater in this aquifer is in the ballpark of around 15,000 cubic kilometers, while the current extraction rate of the countries is in the range of 2.2 cubic kilometers per year. So they have approximately 7,000 years to deplete this aquifer if assuming that their extraction rates are sustained. All right, so just to appreciate those examples, this is the Guarani aquifer system, right? So this is the whole aquifer system, This is a map of the hydraulic head of the aquifer. Okay. So normally, when you are on lower elevations, all right. So when you are in lower elevations, all right, there is a lot of water from the higher elevations that are acting upon in these areas. Okay. So the areas in lower elevations are under a lot of pressure. Okay, so these lower elevation areas have the most hydraulic head. Okay, they're under a lot of pressure. Okay, and you can see here that the flow of water here is going mostly from south from from southwest to northeast. Okay, and this is the Nubian Sandstone aquifer system in northern Africa. And this is a map of the transmissivity or the ability of your aquifer to transmit water. Alright, so transmissivity, to reiterate, is a function of your aquifer thickness B times your hydraulic conductivity. Okay, and you can see here more or less larger transmissivity in the western area. So this is your western area. Okay, and this is attributed to the thickness of the formation in this part. Okay. Now let's talk about your carbonate or your karst aquifers, or your limestone areas, and your mostly limestone areas. Now karst or limestones, uh, actually karst is not exclusively all about limestones. Karst also include your other types of rocks that are susceptible to solution, like your gypsum, uh, halite deposits. All right, but most of the time, karst, the most common example of karst is your limestone areas. So karst can have dual to triple porosity. All right, so they have up to three types of porosity. So first is their matrix porosity or their primary porosity, or the porosity due to the grain spaces. They also have secondary porosity due to fractures or your discontinuities. And their third porosity is due to the karst conduits or the solutions or the sinks within your rock. Okay, so these are highly porous and these are materials with really high effective porosity and really large openings. Okay, so you can expect water or groundwater in here to travel really fast. Okay, so these involve really high velocities. And the problem with high velocity flow of water is that they have a more or less an erratic behavior. So they become non-laminar and they become turbulent, as you can see in the GIF here. So your turbulent flow will involve particles or water particles and sediments that are uh, orbiting around and going at various directions, sometimes even opposite of the flow direction. Okay? And it's really and in the perspective of groundwater or hydrology, it's really difficult to estimate the individual velocities of your particles here. For example, if you have contaminants, they can go everywhere. Okay? As opposed to your laminar flow, where you have more or less well-behaved movement of your water particles. Okay? They're easily predictable, and they are within the realms of your Darcy's law. Okay? So laminar flow is can be easily approximated by Darcy's law, but for turbulent flow, which is present in your karst aquifers, okay, so Darcy's law is invalid for turbulent flow. Okay, so it's difficult to apply Darcy's law for your karst aquifers, and in turn, it's really difficult to understand and model your karst aquifers. Okay, so if you have a difficulty understanding or modeling something, it's even harder to manage that resource. Okay. All right. Another feature of karst aquifers is that you can have highly erratic uh, elevations in water table. Okay. All right. Now this is an example of a karstic limestone. All right. So you can see here it has a more or less rough surface. All right. So you have matrix porosity here due to the pore spaces, and you also have your solution openings or your karst conduits. All right. Right, so this example has a hydraulic conductivity of approximately 304 meters per day. Imagine that. I mean, that's a lot for when you're talking about groundwater velocity. Now, these are the further discussion on the characteristics of regional groundwater flow in karst. So take note that when we are talking about groundwater divides, normally when we are talking about non-karstic aquifers, right, it's easy to estimate the groundwater divides or the groundwater flow paths. All right, they just typically follow the topography, right? But in the case of karstic aquifers, most of the subsurface water flow path will not coincide with your surface water or your topographic divides. Okay, so they can go against what you would expect from the topography. And this is mainly due to your sinkholes or your sinks. Okay, so you have a lot of sinks and a lot of holes in your rock where the surface water can enter. Okay, so water can easily just enter from anywhere when you are talking about karst. Okay, so typically the topographic water divides are not followed when we are talking about karstic aquifers. The second point is that karst aquifers involve really high velocities, right, in the order of hundreds of meters per day, and of course they are not subject to Darcy's law anymore, so they are actually difficult to predict properly. And the third point is that the discharge of water can be localized and they can also be really erratic, right? Simply because karstic areas have a lot of exits. They have a lot of solution openings that can act as spring outlets.
So more or less water can exit from anywhere. Okay. So that's the problem with cars is that water can enter from anywhere and they can also exit from anywhere. All right. So understanding karstic aquifers is done mostly on a case-to-case basis, starting with regional examples or regional starting with karstic aquifers that are more or less similar to the region that you are investigating. Okay, so these are different author. These are a lot of studies that focus on different types of aquifers. All right, and I won't be discussing those karst aquifer types anymore, but you can refer to these studies. All right. There is one important type of karstic aquifers, which are your thick, young coastal carbonates, and these are mostly present in island areas like Jamaica, Cuba, islands in the Caribbean, in Mexico, Bermuda, and even in Cebu, Philippines, as well as Sri Lanka. All right, so these are areas with low-lying coral islands, and these areas can be quite problematic in a sense that, right? So these cars, as you will remember, have a high porosity, so they can have a high infiltration rates, and in turn, when you have high infiltration, it means that you're having a lot of recharge, right? So you have a lot of groundwater recharge, but the consequence of this is that you don't have a lot of streams in that area. So in turn, the population or the local populace will tend to rely heavily on groundwater for their water supply. Okay? And so the populace will rely a lot on groundwater, and consequently, any surface contaminations can easily seep through into these groundwaters. So the other consequence of high infiltration rates is that you can have a rapid spread of contamination in these areas. Okay, so the compounding effects of fast spread of contaminants, the higher reliance of the populace on groundwater, so they compound together, and they can also eventually lead to saline intrusion or saltwater intrusion in the future. Right? And this is just a diagram of uh, an aquifer in Cebu. Right? So this is your Karkar limestone. Right? So you have your recharge from upland runoff, and you're also getting recharge from direct precipitation. Okay? All right. Now let's move on to the other type of so basaltic and other volcanic rock aquifers are more or less also considered as sedimentary rocks in the perspective of hydrogeology. I mean, technically, volcanic deposits are still deposits. They're still sediments. All right, so sequences of tuff, ash, basalts, and alluvial deposits. All right, so that's your typical sequence when you are talking about volcanic rock aquifers. So you have alternations of tuff, your ashes, your basalts, and your alluvial deposits. So why? Note that volcanic eruptions, all right? Volcanic eruptions dump a lot of sediment, so they tend to change your stream networks. Okay, so you tend to have here in volcanic areas, you tend to have stream networks that are rapidly changing, and you also have a lot of debris flows from your volcanic sediment. So you can expect a lot of reworking and more or less transported sediments in volcanic areas, right? And their geologic behavior is close to that of sedimentary rock aquifers, meaning they have a lot of effective porosity. All right, and tuff and ash, for example, have a lot of primary porosity, which is similar to that of your unconsolidated sediments. In the case of basalt, basalt also has a lot of primary porosity, which is mostly located at the top and bottom of your flow layers. So essentially, these are your chilling margins. So the cooling margins of your basalt, right, have a lot of primary porosity. And also note that the permeability of your basalt is just highly dependent on how it was formed. All right, if you have basalt that was rapidly cooled, as in the case of pillow basalts. So pillow basalts are lava that entered water. Okay, and what happens in pillow basalts is that you have blobs of basalt that are forming. They form pillows, and they are essentially surrounded by cooling margins, which have high permeability or high effective porosities. What also influences the permeability of basalt is the number of interflow zones, or the fingers or the layers, as well as the thicknesses of your flows. So typically thin layers of basalt, or rather multiple thin layers of basalt, can have really have high permeabilities compared to a single thick basaltic flow. All right. This is an example of a volcanic rock aquifer in Hawaii, right? You can see here the cross section of the aquifer, more or less. This is the whole aquifer system, and you can appreciate here how the intrusive dikes are impounding water in here. They're serving as permeability barriers, and you also have formations that perch groundwater. So you have ash beds that are acting as permeability barriers. So they perch the groundwater in this area. All right. While the erosional feature of this volcanic formation is acting as the outlet for the springs of this aquifer. Another example here is in India. All right, if you're familiar with the Deccan Traps, which is located in the Deccan Plateau of India. So this is the Deccan Traps in India. It's a huge formation, and this was responsible for one of the major geologic events in our geologic history, right?
Right, you can see in this photo that your volcanic rocks are mostly subhorizontal or nearly horizontal. And in Deccan traps, the groundwater here are occurring just below the weathered rocks. Alright, so these are your weathered rocks, and this is your water table. What they do here is they dig a shallow well, alright, so that it can tap out water for them to extract. Now let's move to the last type, which is the fractured rocks group. Alright, fractured rocks or hard rocks or crystalline rocks. These mostly involve or comprise your igneous and metamorphic rocks that are crystalline. And as you would expect from a crystalline rock, so by crystalline you don't have primary porosity. And the only way you can get porosity in crystalline rocks is mostly by discontinuities. So your foliations, joints, fractures, and faults. Alright, they bestow permeability to your rock. And typically these types of aquifers have yield only small amounts of waters. Although there are certain areas in these aquifers where you can get concentrations of groundwater. The importance of hard rock or crystalline rock aquifers is that there are certain localities where your only source of water are these crystalline rock aquifers, right? And it has been studied before that the transmissivity or the ability of the aquifer uh, to transmit water is highly dependent on the number of your discontinuities as well as their interconnectivity. Okay, so what affects interconnectivity is of course the intersections of your structures as well as the presence of fault gouges. Okay, fault gouges are your clay silt infills in your faults, and of course when you have clays and silts in your faults, what they do is they act as sealants. Okay, and normally you only get fault gouges when you have faulting in an area that is intersecting typically shale formations or highly weathered formations. Okay, so when a fault intersects those layers that contain silts or clays, then you can have fault gouges in your faults. All right. So aside from analysis of your structures, you also have, of course, your surface geophysics, such as your resistivity and electromagnetics. Now, this is just an example of a crystalline rock aquifer in France, right? Note especially this area, all right? So you have a dense formation of fractures here and here, and they are mostly already controlling the shape or the boundaries of your aquifer, right? So that shows how your density of fractures can control the geometry and, in a way, the flow direction of your groundwater. Right? Thanks for listening.
concludes the lecture for this session.